Hello, in this lecture we will fit a couple of linear models, starting with the simpler ones, and then we will gradually increase predictor variables as well as the responses. We will not talk about the testing and confidence intervals, as we already know the distribution of each of our parameters, so we can derive tests and confidence intervals in the similar manner as in the previous lectures. Okay, so let's start with fitting in Excel the simple linear regression model. So where we have only one predictor and one response. And to do so, instead of the formulas that we used in univariate case, these formulas are here to estimate the unknown parameters, we will instead use our formula that is derived in multiple linear regression model and the matrix form. So we want to estimate using this estimator. So we will use cat beta defined like that. Let's go back to Excel. Okay, so we're here. What we need first is our Z matrix. Let's call it Z instead of X. So what we need is our values from here. And then we also need a first column to be only ones. That column is column for the constant, because the model will look something like beta 0 plus beta 1 z. Right, so that is how our model is going to look like. So those parameters are unknown and we want to estimate them using the formula from the matrix form. So we know that we have only two unknown parameters that we need to estimate, right? Beta 1 and so let's write it. Beta 0 plus beta 1 z plus so on. And we need to get some kind of line, so get beta 0 plus beta 1. Right, so let's see how we can obtain this beta with hat and this other beta 1 with hat. So we will get only two values. The matrix form tells us that we need to multiply four matrices, right? So let's first multiply and find inverse, matrix inverse, right, of matrix multiplication. It says transpose Z times Z. So this is our matrix Z. So let's go transpose it. And then itself. So we multiply those two matrices and find the inverse. So this should be not 2 times 1. I wanted to multiply it once, but instead let's first compute step by step. Let's transpose z to the power of -1. Let's call it this, and this is our z. What else we need is our z transposed y. Right, so z transposed matrix multiplication transposed z. And what is our y? Is this vector here. So our response data. And in the end, what we need is our, let's call this first sentence y, and our hat beta. So as a vector, this is what we get, the estimates. So it is not now the estimator because we're using data to estimate those unknown parameters. We need to multiply this matrix with this one. So the second one is a vector. This is what we get, right? As you would probably guess, there is also a function in Excel that gives us those two estimators. But that function gives us much more information. So here we have two unknown parameters, beta 0 and beta 1. So we will select two columns, and then we need to select 5 rows because the function returns that much values we'll see now. So known y's are first, then known x's or z's in our case. And do we want a constant or not? We want the constant, so this is our beta 0, we'll say true. And do we want additional properties of regression statistics? And so we'll click yes. Okay, so first what we have here is our hat beta 1, the first one. The second one is our hat beta 0. As you can see, the values are the same as what we got here. If we would have more beta 2, beta 3, we would need to select more columns, right? Before continuing to see what are the rest of the numbers, let's first interpret those two. So here we have a line, right? Beta 0, beta 1, our estimated. Okay, so let's see how we can check what that line actually is. Just to do quick analysis, I will move ZY for a second. Then right click, quick analysis. You will see charts and find scatter. Okay, so this is our scatter plot of the data that we have. Yeah, I selected a little bit. And what we get here, when you click on the plus icon there, you can select trend line. Okay, that trend line is actually the line that we obtained here. So this line that you now see here is our line y equals to hat beta 0 plus hat beta 1 z using these two numbers. Hat beta 0, as you probably remember, is called the intercept, and this is the slope of the line. We can say that this line approximates the data in the best possible way. So you cannot get a better line to fit this data in terms that you have the minimum squared error. In general, before you fit any model, you would like to check if that model is actually good for the data that you have. In this case, from the scatter plot, we see that we can actually fit the line, even though that we would need more data in practice and similar, but here we can see that this line would fit the data very well. We can now see what are the rest of the numbers that this function gives us. So for example, this number here, so below our hat beta 1, is our standard error or standard deviation of our estimator beta 1. So this is what we get. And this is standard error or our hat beta. Okay. We can always manually compute those values. So for example, the variances. The easiest way is to compute the covariance matrix. So we know how does it look. So covariance of our estimator. It's sigma squared, and we need this matrix times sigma squared. But we would need to estimate our sigma squared as well using the data. And we know what is our unbiased estimator, our S squared. So in order to get our S squared, which is the first thing that we need because we already have this to obtain the covariance structure, we need our error, our residuals. To compute the residuals, so residuals is a vector, right? We need our y minus z at beta. So z, we need matrix multiplication of our z and our at beta, so our estimated values. Okay, so this is our, let's call it at epsilon. Okay, and to compute now the estimate of our variance, so our S squared, this is a number, we need matrix multiplication of transpose hat epsilon, then hat epsilon. Okay, and then we just need to divide it with n minus r plus 1. So our n is 8 minus 3 plus 1, 2 plus 1, 3, because we have, let's write it like that. So this is our estimate of our variance, and we know that it is unbiased. So to get our covariance of het beta, so covariance matrix is going to be 2 times 2, right? So we need to multiply s squared with our matrix z transpose z to the power of minus 1. So this is our covariance matrix. What do we have on diagonal? So this is variance of this one. This is covariance between these two, right? It is symmetric as it should be. And this is variance of this one. So the first one is of 0, the second one is of 1. So what would we expect for the standard error to be? So it is square root of this one. We expect this to be 0.6436, but it is not. Probably a mistake here. Let's see. Yes. So instead of, I wrote that r is 2, but actually we have only 1. So only 1. R plus 1. Okay, so it is 0. So we get that this is the same number, and square root of this should be equal to this, right? And now we know that this is correct, and we know what is the covariance, right? So you can use this, for example, for confidence intervals for either het beta or het beta 0, or if you need to compute the value of the test statistic, so the same way that we usually do. Next, what we have here is first this one. This is our standard deviation of our y, so the estimated standard deviation, it should be square root of this one. So this is equal to this. Those two are equal. Then this is our coefficient of determination, but before we go to coefficient of determination, let's explain those two values. So the first one should be the regression sum of squares, and this one is the residual sum of squares. I will write it more nicely so you can follow it. So regression sum of squares, so it is our fitted values minus our average squared and then sum. Okay, this is something that we had in universe case as well. And this is residual sum of squares. Okay. Then this coefficient of determination, this one, can be obtained as regression sum of squares divided by the total sum of squares. Total sum of squares is, so total sum of squares about the mean is this one, so 42. And the coefficient of determination is when we divide this regression sum of squares with total. So this is our R squared coefficient of determination. As coefficient of determination is close to 1, there might be a linear relationship between the z's and y's. However, we would like to test that as well, so we need another numbers. So we need our value of the Fisher test statistic, and we need degrees of freedom. However, to do appropriate tests, we would also need alpha, or our significant level, and we can compare our value of the F statistic with our critical value and decide if there is linear or not linear relationship, or just relation. So this is just our simple linear regression model fit. Let's go, before we go to another problem, let's call this problem 1. To have different name. So what are we going to do now is fit a couple of different models using the data that we have here. Before doing that, I will copy everything from the first problem. So this is the model that we wanted to fit before. Let's now, instead of this one, we want to fit a model without a constant. Okay, so it is still linear model, right? Because our beta is not squared or something. So just this model. What should we do in this case is basically just change our matrix Z. So instead of Z to have those ones, we will just remove them. And then we will get our estimate. So because now we have only Z is not anymore n times 2 matrix, some of the values we are not going to need. So in this case, we just get only, as expected, only one estimate, which is of beta 1. So we get hat beta 1. We can always check that. So we need now just the constant, so only one. We will use our leanest function. So we select y's, we select z's. Now instead of true, we will set false. So we do not want that constant. And we do not need any more information. We just need the constant. Yes, but first I need to change this one. So what is our z transposed? Z to the power of -1. We have only one value, right? So it should be that one. Yes, but this computes something else. So what we need is actually only this one times this one, right? Okay, so we have only our hat beta 1. So this is our value. I wanted to do it fastly, but it took more time than expected. So in this case, we are fit to our data only one. So we get only one unknown parameter and we estimate it. Right, so we get this other line without the intercept. Let's fit some other model. I will copy the data once again. So say that we want to fit model with natural logarithm of our z. Okay, let's fit this model. Okay, so instead of values z, we need natural logarithm of z, right? Okay, so those are our values and it will automatically change because we only need to change those values to get our estimate. So we get our hat beta 0 and hat beta 1 the fast way. So our model will look like this. So we would still have a line, but with note that this z should be actually our natural logarithm of z. So if we would like to compute the value. So it turns out that it's the same as if we would fit this data to our y's. So if we fit this data and y, okay, we would get our line. So instead of logarithm, we would have z. But for z, we would consider this data, the logarithm one. Okay, so it's not that hard to fit some kind of this model. However, if we want to fit model, such as natural logarithm of beta 1, what we would get is non-linear model. So this is not linear in beta, so we cannot fit it using our method. Another interesting type of linear model is polynomial regression. Just to note that to fit any of those models, it might be easy to estimate these unknown parameters, but still you should check a lot of different things to see if the model is adequate for your data. So let's see how to fit a polynomial regression. So instead of So what we have here is z. We have z, then we have plus beta 2 z squared. Okay, for example, this can go much more. So instead of 2 degrees, you can have up to z to the power of n, or at beta 2 z squared. So I guess that you can guess how to obtain this. So we would need, instead of here, we would need z anyway. But here, values, we would need z squared. Okay, so by squaring those and changing, now what is going to be our matrix z? It is going to be 3 times 3 matrix. So we can remove this. Or maybe instead of removing, we can select everything and just move like this. See what will happen. Yes, it should work. Then this one should be 3. Just. Okay, so only our matrix Z changes. And here we have estimate of each of our unknown parameters. Note that we also have variance here that is also unknown and needs to be estimated. You can see and check what actually happens with that one. So you can play with this. You can even remove those two and have only this over here. So beta 2 z squared. You can have whatever you want. But usually you won't get a nice fit. With polynomial regression, for example, it is easy to overfit a model. So you know that through, for example, those points, you can always fit a polynomial. So if you have, this is from analysis, if you have 5 points, you can always fit a polynomial through those 5 points. But this will result in overfitting, and the model is not going to be very good. So model checking is another important thing in general, not just in regression. I believe that after this, it would not be really hard to fit a simple multiple regression model where we have now 2 variables that are different. Okay, here we had only 1 variable, but we squared it, for example, or found natural logarithm. But here we have 2 variables. But still, we can use matrix Z and our hat, everything. But we would have a little bit more. Here, Z is going to be a larger matrix because we have more observations. We would have beta 0, beta 1, let's call it Z1, and beta 2, Z2. And I'll change Z2, Z2. Okay, so what is our matrix Z now? Depends what we want to do. So let's say that we want to estimate this model. So we have that constant here. So the constant will stay. This is corresponding to beta 0. This one is this is Z1. So we can just paste the value. Okay. So what would be our matrix Z? So the whole, right? And this you can always select again instead of dragging what I do. Okay, so this is our Z. This we need to change again. Okay, I'm not selecting twice. and then we get our estimates. Now to use our leanest function, we have three, okay, unknown parameters, 1, 2, 3, 4, 5, because it returns 5, min, our known y's, and known x's, constant true, and true for additional information. So what we get is 30, 2 point something, and 0 point something. So it is always easy to use the function in R or any other, but you should know how to compute it and what's behind it. This is why we are doing it in Excel, so you can get a hang of this. And the rest is, as you can see, the same as in previous. So you have standard deviation for each of those, standard deviation so of our y's, coefficient, etc. But when you have two variables, you can play a little bit more. So instead of this model, you can just add one more, or let's just remove z1, z2, and put instead of z2, z1, z2. So we would have here, okay, I did not change this, so this is z1, and this is our z2. But here we would have z1 and z1, z2. So it is still easy to compute the estimates, but instead of z2 we would need to multiply those. And then automatically we get our estimate. We can check it, but instead of our z2 we would need, yeah, but I cannot change it unfortunately, so I would need to select again. So what we need is our known y's. Okay, I first need to, yes, so what I need is our y's, known x's, true and false. Okay, so I need to select, because we have 1, 2, 3 parameters, so 3. As you can see, it is the same as what we got here, which is also expected. There is another way to use regression in the tab data. Okay, you can click on data analysis there, and you can find the regression. You cannot see this on the screen, but you can find the regression and do it from there, but it should return the same. And let's go to the multivariate multiple regression, where we have 2 responses and let's say 4 our variables. Okay, so first, as usual, we need our Z matrix, right? So this is going to be our Z matrix. It's the same, so it does not change the matrix. Values, okay. Now our inverse is going to be 5 times 5, right? So 5 times 5. So we have matrix multiplication, transposed, yes, splitting, again Z. This is our inverse. But now, because we have more unknown parameters, so for each of those we have 5. So 5 for first response and 5 for our second response. We would need matrix 5 times 2, right? This is for our transposed Z, and okay, so I need matrix multiplication and our y's, right? So this is what we get, and in the end, again, our 10 unknown parameters are going to be multiplication of this and this, which is pretty much the same as what we did so far. Okay, we probably made a mistake. Inverse. So we have matrix inverse here. Okay, let's check now. So it is the same as if we do two different multiple regressions. Okay, so we'll just check it for one. So let's use this linest function and false. So what we should get, this is equal to this is equal to yes. So this is correct. However, even though those are two multiple regressions, as you can look it, this is just for the estimation of the parameters. Here you have to take also into consideration the correlation between the errors of the models. So here we had only one epsilon, right? But in our case here, you would have two. So you would have for this one and for this one. And those errors are going to be correlated. Okay, so you would have different parameters and everything. Let's write it like this. Because those are only two random variables in the model. So they can be correlated in multivariate multiple regression. This should be taken into consideration when you make some conclusions or confidence intervals or similar. Because in this case we have another assumptions. Okay, but in this case it's a little bit different. Anyway, the goal of this lecture was just to fit a couple of models using data, so you can imagine that this data is whatever you want to test. The computation of confidence intervals and test statistic is the same. I need to mention it multiple times. You can find formulas, but the procedure is more important. In this case, when you have multivariate multiple regression, as it is hard to compute everything by hand, the confidence interval and similar, it is not likely that you can get it on test. At the most, you would need to fit some low number of observations and find the estimates and mention model assumptions and everything that you would need anyway to know the model assumptions and similar. But still it's unlikely. The fourth problem is basically the same, so you can do it for practice if you wish. This will be it for this lecture. Have a nice day. Goodbye.